Standing next to a massive industrial centrifugal pump, you can actually feel the power vibrating right in your
Oh,
chest.
absolutely. I mean, it is thousands of pounds of metal spinning at just mind-bending speeds.
Right. And if one microscopic flaw makes it into the field, well, the results aren't just expensive, they are explosive.
Which is exactly why the inspectors guarding the gates at the factory have to be absolutely uncompromising.
Yeah, and for you listening, joining those ranks is today's mission. We are diving into mastering the API SIRE exam, the source inspector rotating equipment certification.
Yep, you are prepping for a grueling 3.25-hour closed-book marathon.
I mean, 110 multiple choice questions in English with 100 scored. Okay, let's unpack this. We are going to read 5 full practice questions aloud, but we aren't just giving you the
Yeah,
answers.
we are tag teaming every single option A through F so you understand the exact underlying logic the exam demands.
All right, let's hit the factory floor with our first scenario. So the question goes, during an inspection of a centrifugal pump's components, you notice a series of linear indications on the surface of a cast impeller.
Okay, so linear indications on the surface.
Right, and they are visible to the naked eye and seem to align along the casting flow lines. Which of the following is most likely the cause of these defects?
Well, when analyzing the options, you really have to visualize the physics of molten metal. Like, could it be A, shrinkage cavities, B, segregation, or C, cold shuts?
Or what about D, inclusions, E, hot tears, or F, porosity? I mean, is this like baking a cake that cracks when it cools down too fast?
Yeah, actually, the physics are remarkably similar to that. That tension points us directly to option E, hot tears. When molten metal cools, it inherently shrinks.
So it just pulls itself apart.
Exactly. If the rigid mold restricts that shrinkage, the stress physically rips the hot metal apart right along the flow lines. The other choices, like shrinkage cavities or porosity, are usually trapped gas bubbles.
So they're basically voids, not linear tears.
Right. And segregation, cold shuts, or inclusions, those are completely different material mixing issues entirely.
Okay, so we catch the microscopic tears on the metal. But let's say a structurally sound, yet, slightly uneven impeller gets installed anyway. That brings us to our next scenario.
Let's hear it.
In vibration analysis of rotating equipment, which of the following is a primary indicator of potential imbalance in the equipment?
So the options here range from A, increased oil temperature, and B, enhanced acoustic emissions, to C, high axial displacement, and D, decreased rotational speed.
And then there's E, elevated radial vibration levels, and F, frequent seal leaks.
Right, and what's fascinating here is how the exam tests your ability to distinguish a root cause from a delay effect. The answer is E, elevated radial vibration.
Wait, really? But if a massive industrial pump is violently wobbling on its base, wouldn't, hot oil or frequent seal leaks be just as obvious?
Oh, they definitely would be, but those are secondary symptoms. I mean, they happen eventually because the machine is literally tearing itself apart. The exam wants the primary, direct indicator.
So the immediate physical reaction.
Yes, an imbalance means the weight is off-center. As it spins, centrifugal force yanks the shaft outward, perpendicular to the axis.
Okay, I see.
And that specific outward shaking is radial vibration. High axial displacement is shaking lengthwise along the shaft, and acoustic emissions might just be one noisy bearing.
And decreased speed is probably just an electrical motor fault, right?
Exactly. Radial vibration specifically screams mass imbalance.
Okay, we've covered identifying the physical flaws, but this deep dive also needs to cover the corporate safety nets. The API SIRE exam heavily tests those systems.
They really do. Let's look at a quality systems question.
So the text says when conducting an audit of a supplier's quality system, one of the critical elements to evaluate is their process for ensuring that all products and services meet specified requirements. What is this process called?
You'll see options like A, training, B, inspection, C, maintenance, D, documentation, E, calibration, and F, verification.
I mean, those all just sound like mandatory quality control buzzwords.
Well, they are, but verification is the formal umbrella. Think of it this way. Training teaches the welder, and calibration ensures the micrometer is accurate.
And inspection gathers the physical data.
Exactly. But verification is the overarching protocol. It's where someone officially cross-references that final inspection data against the original engineering blueprint.
And legally signs off that they match.
Right, it's the ultimate prove-it step, which makes F the correct answer.
Which leads right into setting the boundaries for that proof. What is the primary purpose of establishing rejection criteria for rotating equipment during the inspection process? Here's where it gets really interesting.
Oh, how so?
Because the options suggest it's A, to reduce production costs, B, facilitate quicker repairs, C, comply with legal requirements blindly, or D, increase inspection speed.
Or E, identify equipment failing safety standards, and F, ensure aesthetically pleasing equipment.
Yeah, I am honestly holding out for an aesthetically pleasing pump.
Well, a fresh coat of paint doesn't stop a rotor from exploding. The purpose is strictly option E, to identify equipment failing safety standards.
So it is all about protecting the end user.
100%. The exam wants you to understand that rejection criteria exist entirely to prevent catastrophic failures. It's never about saving the manufacturer money or rushing the inspection speed.
Or just checking a legal compliance box, right?
Exactly. Safety benchmarks require flawless tracking.
Let's look at our final scenario then. During an audit, you realize a supplier's corrective and preventive action, or KPA, process is not well documented. Which of the following is the best immediate step to take?
A quick note here, KPA is the system a company uses to investigate why a defect happened and how they'll prevent it next time.
Right, so when an auditor finds a broken KPA system, the options are A, accept the system if products look fine, B, halt the audit entirely, or C, recommend an external consultant.
Along with D, suggest a workshop. E, analyze past records. Or F, discuss the issue with the quality manager.
Well, ignoring it is negligent, but bringing the entire factory audit to a screeching halt just feels like a massive overreaction.
Precisely. That's why the immediate step is F, discussing it with the quality manager. As an auditor, your first move is always clear communication.
So suggesting consultants or digging through archives just bypasses that crucial first step.
Yes, you have to directly collaborate with the team on the ground to figure out why the system broke down in the first place.
Okay, so conquering this exam really means understanding the why. The physical tension causing hot tears and the outward centrifugal forces driving radial vibration.
Along with the blueprint matching proof of verification and understanding rejection criteria as life-saving benchmarks.
Right, and prioritizing communication when a safety process fails. If you internalize those mechanisms, you aren't just memorizing facts.
No, you're actually ready to protect the field.
Which leaves us with a thought to mull over. If we step away from centrifugal pumps for a second, how might applying this rigorous formal verification mindset expose hidden vulnerabilities in the daily systems you rely on in your own career?
Especially when you prioritize direct communication when a process fails.
Definitely something to think about next time you blindly trust a process.